Hi, this is Alex from devstories.eu. AlphaFold 3, Protein Structure Prediction, Episode 12 of 21. Predicting exactly how a new drug binds to a target protein feels like a breakthrough, right up until you realize the AI just placed two solid carbon atoms in the exact same physical space. A beautifully rendered structure is useless if it defies the laws of physics. Today, we cover interpreting AlphaFold 3 results to help you separate biological insight from computational hallucinations. AlphaFold 3 generates a three-dimensional coordinate file along with a set of specific metrics. Evaluating a result requires reading these metrics together because a high score in one area can mask a catastrophic failure in another. First, you look at local confidence using a metric called PLDDT. This grades every single atom or residue on a scale of 0 to 100. A high score means the model is very certain about the specific local geometry of that chain. But local confidence alone is not enough. You can have a perfectly predicted protein and a perfectly predicted small molecule ligand that are floating independently in space. To know if they actually interact, you must check the predicted aligned error, or PAE. PAE measures the expected position error in angstroms. Lower numbers are better. When you predict complexes, like a protein binding to a DNA strand or a drug molecule, you focus on the cross-PAE. Think of the PAE output as a heat map matrix. The diagonal shows how confident the model is about a single chain's internal structure. The off-diagonal areas show the confidence between different entities. If the key AE between your protein and your ligand is low, AlphaFold is highly confident in their relative positions. It strongly believes the ligand sits exactly in that specific pocket. Here is the key insight. High confidence does not automatically mean physical reality. AlphaFold 3 is a deep learning model, not a molecular dynamics simulator. It prioritizes spatial patterns over strict physics. This brings us to the clash score. Because AlphaFold 3 models ligands, nucleic acids, and modified residues directly without a strict physics-based relaxation step, outputs can contain severe steric clashes. A clash happens when two atoms are assigned coordinates that place them impossibly close together, effectively overlapping. The server calculates and provides a clash score for your output. A high clash score is a massive red flag. Consider a scenario where you analyze an output and the main protein chain has a PLDDT over 90. The cross-PAE between the protein and your target ligand is very low. Interface metrics suggest a strong, confident binding event. On paper, it looks like a perfect docking prediction. Then you check the clash score and it is highly elevated. If you load the physical coordinates into a viewer, you will see the ligand passing straight through the protein backbone. The neural network recognized that the ligand belongs in that general binding pocket, but it failed to route the atoms around the existing side chains. It hallucinated a ghost molecule that ignores solid matter. When you evaluate an AlphaFold 3 result, you must check structural confidence and physical realism simultaneously. Use PLDDT to verify the shape of individual molecules. Use PAE to confirm they interact where you expect them to. Then check the clash score to ensure the model has not violated basic chemistry to force that interaction to happen. Remember that a deep learning model outputs a spatial hypothesis based on pattern recognition, so a highly confident prediction is only valid if the atoms actually respect the laws of physics. That's all for this one. Thanks for listening and keep building.